We have all already observed small waves in water. These travel at a finite speed in such a way that we can follow their propagation. These waves also carry information about the flow, such as the boundary conditions, for example. In this lesson, we will discuss this wave propagation and the link with boundary conditions. So let us consider this channel, with a gate here at its downstream end. If the gate is moved to reduce the discharge below it, so it is slightly closed, a surge wave is generated here that will travel in the upstream direction at a speed a. To analyze this situation, we will consider a volume moving with the wave. So we thus express the relative velocities v1 plus a and v2 plus a as we follow the wave a. The considered volume is sketched as illustrated here, and on this system we will write the Euler equation that requires the evaluation of the forces and of the increment of momentum in the considered volume, that is our control volume. Assuming a horizontal, frictionless, unit width channel, rectangular channel with parallel flow upstream and downstream from the wave, the only forces to be considered are the hydrostatic pressure forces represented here. So the left-hand side of equation 1 that expresses the forces is developed in the flow direction, that is the horizontal x direction. Then the momentum balance is in fact the difference in momentum between a volume A prime, B prime, D prime, C prime and volume A, B, D, C here. As the volume A prime, B prime, D, C remains unchanged, this difference can also be expressed like this here. So finally, equation 4 is developed as follows. Rho H2 V2 plus A delta T represents the mass in the volume C, D, D prime, C prime. And this mass moves at a speed V2 plus A. The last term here is a similar development for the volume A, A prime, B, B prime. We can now combine equations 2 here and 5 to write the momentum balance of equation 1, and we obtain this result. Using the continuity equation 7 here, we can replace V2 plus A in equation 6 after simplifying by rho delta T. Then we can develop this term here and simplify H1 minus H2 that appears on both sides of the equation to finally obtain equation 10. From equation 10, we can express the propagation speed of the wave. If we now consider an infinitesimal wave, H2 is very close to H1, so that we can simplify different terms and we can write equation 11 as follows here. Remember, we have defined the wave speed A as positive towards the left, while the other velocities were defined as positive towards the right. If we adopt the same positive direction for all the velocities, including the wave speed, we obtain equation 14 here, which is the general formulation for a wave speed. The wave speed is composed of two parts. First, we have v, which is the water velocity, the driving velocity, and then the celerity of the perturbation, c, that is equal to square root of gh. If the water is at rest, as illustrated here, waves will travel at the same speed in all directions, as we can see here for the drop falling in still water. The expression here that we just obtained for the celerity can be generalized to any cross-section using the definition of the mean depth that is recalled here, and accounting also for the bed slope. So, in fact, this term that we just wrote here is exactly the denominator of the Froude number that we have introduced in a previous lesson. So the Froude number is actually the ratio between the flow velocity and the wave celerity. If the Froude number is equal to 1, this means that the flow velocity is equal to the celerity of information, or that is the velocity of waves traveling in the flow. So we can write this equality, or this one, using the definition of the mean depth. Rearranging the terms, we find this expression that we already know, and that expresses the definition of the critical depth. So we can conclude that a flow at a critical depth corresponds to a flow at a velocity equal to the propagation speed of information in the flow. All the information we have collected to classify the flows using the critical depth is summarized here. If the water depth is larger than the critical depth, the flow is said to be subcritical, as the flow velocity v is smaller than vc. So as a consequence, the Froude number is smaller than 1, and this means that information can travel both in the upstream and in the downstream direction. Therefore, the flow is said to be controlled by the downstream condition. This means that if something happens at the downstream end of the flow, like a gate that is moved or a change in the downstream level, this information will be able to travel in the upstream direction and influence all the flow. On the opposite, if the water depth is smaller than the critical depth, the flow is supercritical, which means that the flow velocity is larger than Vc and the Froude number is larger than 1. The information can thus only travel in the downstream direction, and therefore the flow is said to be controlled by the upstream conditions. This means that if there is a change of condition somewhere downstream in the flow, this change will not be able to travel back in the upstream direction. And then, of course, we have the case when H is equal to Hc, which is the critical flow defined by Froude number equal to 1. In summary, we have seen in this lesson how the critical regime can be used to classify the flow in subcritical or supercritical. We have seen earlier that it was also possible to distinguish between mild and steep slope, comparing the normal and critical depth. So this concept will now all be combined in the following lessons. Goodbye!